We're going to take a look at question number 1C and look at how to write the repetitions of non-permissible values. So the first thing is we need to recognize where we're going to get non-permissible values is whenever we have a divide by 0. So anywhere there's a denominator, we need to look at the possibility of that equaling 0. So cotan has a denominator, so we have to worry about that. And we also have to worry about the 1 minus sine x being equal to 0. So first of all, I'm just going to rewrite the cotan. The cotan is going to be cos x over sine x. Okay, so, and maybe I will just color code that, and this is where that cotan is. And then we have a 1 minus sine x, and then we're going to worry about that separately. Okay, so there we're going to need to look at when the cotan has a divide by 0. So that is when the sine x is not equal to 0. Okay, and then solving for x, sine x is equal to 0 at this point 0 and pi, and so x cannot be equal to 0, pi, 2 pi, dot, 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 dot. Okay, and there's actually repetitions of this solution. In fact, if I take a look at the graph of this, if I take a look at the graph of the original cotan x over 1 minus sine x, you can see that at pi, so pi is here, there is a vertical asymptote, a non-permissible value. At 2 pi, there's a non-permissible value. At 3 pi, there's a non-permissible value. And these are just repeating at 0, negative pi, negative 2 pi. Okay, so there are infinite number of solutions here. And to show the repetitions, rewrite it in this way. So x is not equal to, we're just going to have repetitions of pi. So I write it like this, pi times n, or n pi, and then n is an integer. That symbol represents integers. You can use I if you like, but that means that n can be negative 2. Well, that means I have negative 2 pi. It could be negative 1, which at negative pi could be 0, 1, 2, 3. And then this n represents how we can express the repetitions, the infinite repetitions of this solution. So this is how repetitions are written, using this n with an ne, looks like a z. That represents integers, and maybe I'll make that sure that's clear. That represents integers. Okay, so that's the repetitions for that. Notice that there are also other vertical asymptotes in here that are non-permissible values. Okay, if I take a look at my graph, there's one at pi over 2. Okay, there's one at 3 pi over 2. Oops, that's not 3 pi over 2. There's one at pi over 2, and then the next one's occurs here at 5 pi over 2. And those blue ones are separated by 2 pi. Okay, so if you look at this one here, that's going to be at negative 3 pi over 2. So the spacing that's different than the black ones, and that's based on the other restriction, 1 minus sine x. So I'm going to solve for that as well. So I'm going to say that 1 minus sine x is not equal to 0. That means that sine x is not equal to 1. Okay, so where is sine x equal to 1? It's only happening once every revolution. It's going to happen there. And to write this, we can write this as x not equal to pi over 2. And then we got to go around the full circle to 5 pi over 2. And then another full circle to, we're going to end up at 9 pi over 2, dot, 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 dot. And so to show these repetitions, instead of writing all this dot, 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 we're going to write this with repetitions. And we're going to start at pi over 2. And then we're going to go increments of 2 pi, where n is, again, an integer. Okay, write that a little bit nicer. n is an element of integers. Okay, so again, this part here shows the repetitions.